Let's jump right in. You probably already know that solar panels generate electricity, right? But today, in this explainer, we're going to trace the exact, highly engineered journey of a single, solitary photon. We're talking from the absolute vacuum of space through microscopic atomic collisions straight into your home's electrical grid. There is no magic here, it's just incredibly elegant physics and engineering, and we are going to break down the whole shebang step by step. Okay, let's kick things off with a totally staggering sense of scale. Just 1 hour, literally 1 hour of sunlight hitting our planet, contains enough photons to theoretically power the entire world for a full year. That is massive. Our sun is essentially this giant, natural nuclear reactor that's constantly shooting out tiny packets of energy. If we can capture even a fraction of what hits the Earth, well, it completely changes the paradigm of how we power our lives. So you see these familiar rooftop systems? They are perfectly designed to harvest that massive cosmic potential right above our heads. Now, they might look like simple, passive sheets of glass, but actually they're heavy-duty, highly engineered devices. Think about this. A single, typical panel is about the width of a twin mattress and weighs around 30 pounds. And since most homes need anywhere from 15 to 30 of these, a standard array is quietly pulling down astronomical amounts of energy right into your electrical panel. But getting to that sleek, finished product, that requires some intense precision and extreme manufacturing conditions. The process actually starts by purifying mined quartz in these extreme heat furnaces to get solar-grade silicon. Then, that silicon is melted and pulled into solid crystalline ingots, which are meticulously sliced into razor-thin wafers. And they use diamond wire saws to do this. Next, we add anti-reflection coatings and super precise electrical contacts so the current can flow. And finally, these cells are electrically wired together and sealed under tempered protective glass with a tough aluminum frame. It's built specifically to withstand the elements for decades. Once those panels are up on your roof, they just wait for the sun. The actual journey of solar power starts with a single photon traveling 149.6 million kilometers. It's a crazy trip across the complete vacuum of space, and it takes about 8.5 minutes before it finally strikes a silicon cell. Just imagine that incredible, monumental distance ending precisely on your home, just to boil your morning coffee or power up your laptop. This brings us to the core mechanism, the real atomic magic, the photovoltaic effect. When that photon collides with a semiconductor material, which is typically monocrystalline silicon, it transfers its kinetic energy directly to an electron. That sudden, precise burst of energy violently breaks the electron free from its atomic bond. But wait, a loose, floating electron isn't usable power just yet. To get electricity we can actually use, we have to force those free electrons to flow together in a specific, unified direction. So how do we force those loose electrons into a usable electric field? Well, the cells rely on a highly specific junction between two distinct layers of silicon. On one side, we have the N-type layer, which is treated, or doped, with phosphorus to give it a surplus of extra electrons. On the flip side is the P-type layer, which is doped with boron, leaving it with fewer electrons. This built-in atomic imbalance creates a permanent electric field right at their junction. When a photon knocks an electron loose, this field acts like a microscopic slide, instantly forcing the electron to flow in one specific direction through an external circuit. Now, this specific one-way flow of electrons from the N-type to the P-type layer creates direct current, or DC. But here's the catch. Our modern homes and the broader electrical grid actually operate on alternating current, or AC, where the flow of electrons periodically reverses back and forth. This creates an immediate mismatch between the steady, unidirectional power your roof is producing and the oscillating power your household appliances actually need to turn on. That fundamental mismatch is exactly why we need a device called an inverter, which is basically the brain of the entire operation. It acts as a vital technological bridge, functioning as a translator. It takes that steady flow of DC power and uses advanced solid-state transistors to rapidly flip the electrical direction. This synthetic oscillation creates a clean, repeating AC sine wave that is perfectly synchronized to the frequency of your local utility grid. That makes it instantly safe and usable for your lights, appliances, and all your devices. When designing one of these systems, you actually have two main choices for that brain. You can either use a central string inverter for your entire roof, or you can attach microinverters to each individual panel. With a central string setup, the panels are wired in series. That means if, say, a chimney or a tree shades just one panel, the output of the entire string bottlenecks and drops to match that one shaded panel. Microinverters brilliantly solve this vulnerability. They optimize power at the individual panel level, ensuring that every single panel performs at its absolute maximum potential, entirely independent of what's happening to its neighbors next door. Okay, so solar is incredibly efficient at high noon on a clear summer day. We know that. But right about here, you might be wondering what actually happens to your home's power production when thick clouds roll in or when the Earth rotates and the sun sets entirely. Let's break down how modern solar architecture handles these inevitable real-world conditions. First, let's look at overcast weather. During cloudy days, your panels are actually still generating power by capturing diffused, scattered light. Solar irradiance is made up of both direct light, those clear, intense beams, and diffuse light, which has been scattered by clouds or atmospheric particles. Your panels are highly sensitive and they efficiently collect those scattered photons. So while overall output can be reduced by 10 to 25% or maybe up to 60% under really heavy overcast skies, your roof absolutely does not completely clock out just because of some gray weather. Nighttime, however, is a totally different story. Since panels produce zero power at night, homes rely on either storing their daytime excess in local batteries or using net metering to trade electricity seamlessly back and forth with the utility company. With a modern lithium-ion battery system, you physically store the surplus energy your roof generated at noon so you can run your television at 8 p.m. With net metering, you essentially use the broader grid as a massive battery. You send your excess power to the utility during the day, literally spinning your meter backward, and then smoothly pull power from the grid at night. Ultimately, you only pay for the net difference. But what's truly fascinating here is how these localized rooftop systems are actively improving the broader electrical infrastructure. Far from just being passive power sources, modern smart inverters dynamically support the entire electrical grid by providing critical services like frequency response and reactive power. Historically, we relied on massive spinning steam turbines at centralized plants to stabilize the grid through sheer physical inertia. Today, advanced solid-state inverters can digitally mimic that exact stability. They instantly adjust output to correct frequency drops, they sync voltage and current to eliminate power waste, and the absolute most advanced models even act as grid-forming units. That means they're capable of black starting and restarting a downed grid after a major outage. So we've traced a photon across millions of miles into a silicon wafer, through a localized inverter, and out into the modern grid. We are actively transitioning from a world that extracts finite fuels from the ground to one that seamlessly harvests an inexhaustible nuclear reactor in the sky. The technology is already deployed on millions of roofs today. So I want to leave you with this final, provocative thought. What will our global grid look like when every single home operates as its own intelligent power plant?